Okay, so this is going to be a pretty short video. Please excuse the condenser mic in the center of the screen, as well, I like good audio with my video. So this is an automotive vehicle troubleshooting board that I originally copied from my ALC course, and then I built upon it and then rebuilt it and added some other stuff to it. So we're going to briefly go over how it's built, what's all involved in this, and then we'll go through a couple of circuits that you can duplicate pretty easily. Number one, power source. So this has a power supply in the back. You can see is this little guy right here, and I don't remember what that originally was supposed to power, but it inputs 120 volts AC and it outputs 12 volts DC with a maximum current draw of 3 amps, which is listed up here. As I turn things on and off, you'll see the amp meter jump up a little bit, not a whole lot, but a little bit. If I wire a ton of stuff in here, we get pretty close to the 3 amp limit, so I may end up backing or stacking power supplies. I've got several of those 12 volt supplies. This one right now is set up to turn our engine, which is mocked up with a computer fan, turn that on using a starter solenoid and our push to start button and our battery ground and battery positive. So when I press that, you can hear the starter solenoid click and our fan turns on. So the point of this board is that I think it's a lot easier for soldiers to grasp the concept of how electricity flows and how it moves through a vehicle if you can break things down into their individual components, and if you can visually see how the flow works as you're hooking the different components together. Soldiers that don't understand electricity really at all, that have no fundamental grasp of how electricity flows through a vehicle, can pretty quickly get a much better idea of how this works. So the components we have on here, we've got 2 brake lights. These are just LEDs that come out of like a PLS or a Hemet or something like that. We've got our ground and positive battery bus bars, which is just wire I've run through and then ran into the ground and then positive on the power supply. This is so you can hook up a bunch of stuff all at once. We had done it with just the smaller screws, but it's hard to hook a lot of alligator clips onto that. So over this system, you have a push to start, which is just a momentary switch on the brake lights or these LEDs we're using. You've got positive and ground there. You've got 2 12-volt relays with the coils listed at 85, 86, your standby voltage on pin 30, and then 87 alpha and 87. We have a blower motor on this side with this is just a selection switch. It's not a potentiometer, just a selection switch. Headlights on and high beams on, and then the middle is off. We have a potentiometer up here. We have a thermal flasher unit, turn signal switch left and right. A brake switch was just a push button momentary, and then high beams on the side and headlights. The engine itself, and then the starter relay. The amp meter is hooked up in the back. The students have no effect over the amp meter. It's just in there so that I can monitor this. The only other thing worth noting is there's a hole drilled down here, so you can see there's a blue LED, and that just tells me that the power supply is plugged in and on. If you flip to the back, you'll just see how this is set up so we can just hang it if we need to. But everything is pre-wired here. I unsoldered the ground to one of the lights because I was trying to see if I could get something to work, and I needed a dummy load, so I wanted that. Didn't actually end up working the way I want. Still got to work around that one. The only thing pre-wired ground-wise is the lights, and that was just to conserve wire. But there's really nothing complicated about this side of it other than you just see how the different portions or different components are wired in. go through a couple of circuits with you. Okay, first circuit I'll touch on, might as well since we already have it wired, is our start the motor with the starter relay and the push to start. So we have battery power runs out to the push to start. From the push to start runs up to the coil activation on one side of the starter solenoid. Ground runs from that coil back down to ground. Now, we also have battery power running up to the standby lug on this side. Output of that runs to the the motor, positive on the side, and then the ground runs back down to earth ground. So when you push the push to start, you're energizing the coil. The coil pulls a metal rod down, and then current's allowed to flow through the starter solenoid to the motor, which then runs back to ground. Pretty simple. Okay, so circuit number 2 is just simply activating the brake lights. So you have positive running out from the battery, runs up to the brake switch sends that power back out to the positive inputs on both brake lights, runs through the brake lights, and then both of the ground wires run back to battery ground. So when we press this, press it just like you would in a regular brake circuit. When you press it, the brake lights come on. Alright, third circuit is high beams and low beams. So how it works, voltage runs out from the battery to the headlight and high beam switch. You got voltage coming in, the voltage goes through the switch. When you click it down, that runs up to the headlights, and then the headlights again are wired to ground in the back. When you flip the switch the other way, same thing. Voltage comes in from the battery, flows through the headlight switch, well in this case high beams, comes in the high beam switch, goes to the switch, comes out, and then distributes out to the high beams. Now, basically this is a three-way switch, right? You got down, middle, and top. What we've done is the voltage in is actually shared to the center input, and then when you flip it down, it just kicks an arm up and that current flows out one side of the circuit. Circuit number 4, left and right turn signals. Battery voltage comes out, goes into the thermal flasher unit. So it comes on top, comes out the thermal flasher into what the same three-way switch that we're using down here, same kind of switch. And then when you flip to one side, it's going to send current out, and then that goes up to the light. If you flip it the other way, it does the same thing. Now, because this is a thermal flasher, this is not a solid state flasher. Those are not super complicated circuits to build, but that's kind of a level above the basics that we're trying to get after here. Okay, circuit number 5, and I'll probably be the last circuit in this video. If you guys want to see me do more of them, or there's one you want to see done, put a comment below and let me know what you want to see. In this one, this is kind of based on Humvee setup. So what we've got, voltage comes out, we're using this relay down here to start the motor. We could use that one, but I'll just use this one instead because this is basically a 4-pin relay. These are 5-pin relays. So you can see the high beam is on. In this particular case, we're going to call this the wait to start light. Now, got it. In a Humvee, once the glow plugs have warmed up, the wait to start light goes off. It doesn't work that way in this case. Maybe one day I'll wire that in, but I'm not too concerned about it for this. So wait light is on. Once you would see the wait light go off, in this case, we're just going to press the button. You can see our relay kicks on, the motor starts to spin, and the light goes off. And that's just demonstrating the difference in use between pin 87 alpha and pin 87. Okay, circuit number 6 and final circuit we're going to build today. What we have is using battery power with the push to start, the starter solenoid or starter relay, the blower motor, which we're going to count as the starter in this design, and then the actual engine itself. So basically power comes in, goes to the push to start, starts to press, current flows through, activates the starter relay. Starter relay has voltage on standby from the battery that flows down to the blower motor. Blower motor flows out to the engine, engine down. Now, got it. Within an actual engine, there'd be no electrical connection between the engine and the starter motor, as this would mechanically engage this and make the motor turn, but I can't do that in this. So again, the process is still the same for them to figure out. And you can see that when we press the button, this motor spins, or spins are a big one. These are both 24-volt fans, so they don't spin super fast on a 12-volt supply, but they will turn. Okay, closing thoughts before I forget half of them. Number one, if you build this thing, the reason I use the 3 amp power supply versus a car battery is that if they get this wrong, let's just say, for argument's sake, that they short this out, which is what this is doing. If you look carefully, you'll watch the amp meter drop. It comes up and then drops. It pegs off. You can see it jump around like that. The power supply sees there's a short to ground as its maximum amperage is trying to be drawn, so it cuts itself off and then restarts. So in a car battery, you got like 1200 standby amps or cold crank amps. That will melt wires in here super fast. This way, I don't have to worry about that. Two, all the labeling we did is basically on an inkjet or a laser jet printer. We print out all the labels, put packing tape over it, rub it real flat, cut out the packing tape on top of the paper, and then we just soak that paper with the packing tape still pressed on warm water, rub the paper off, and the ink gets transferred to the tape. And it makes this a really easy way of making nice professional designs. Originally they were just taped on pieces of paper that labeled everything, and I didn't like it. You will see, you can't see from here, but there are numbers written on every component in blue ink that tells me the number of amps that each component's drawing. So in this case, we've got 0.318 on the starter relay. The starter relay takes basically 1/3 of an amp draw to make it work. I think that pretty much covers everything you need to know about the board. Again, if you want to build one, they're super easy to build, and almost everything in here runs on a 12-volt power supply. Let me repeat that. Everything in here will run on a 12-volt supply, but even components that are 24-volt will run on the 12 volts without too much of a complaint. The only thing that's not hooked up is the voltmeter, because the voltmeter takes like 2.8 amps. I don't know if it's just a bad meter or if it's just old. This is how this was built, or it was built where there was plenty of amps available, so they didn't care. But it draws almost the full load of this. I can't even light the LEDs up with that. Side note, with the thermal flasher, you can't use with the LEDs because there's just simply not enough load from the LEDs to make the thermal flasher flash back and forth. But I think that's everything I wanted to cover with this, so hopefully this was helpful, and hopefully it inspires you to try and build something similar that helps better your soldiers' understanding of electricity. And if you have something that you would add to this, please leave a comment in the comment box below and let me know.